All right, so let's define a term here to leverage the dot product facts that we've produced in the last couple videos. And so here, to cook up this construction, let's imagine you're looking in Rn, good old-fashioned n-dimensional real space, and imagine you've got some subspace of Rn. So this subspace, we'll call it W. This could be any subspace of Rn. It could have any dimension between 0 and n. It could have any basis vectors that you want between a set of 0 elements and a set of n elements. So, I mean, imagine R was 20, you could just take 4 linear independent vectors at random, and then you'd have a 4-dimensional subspace W. W is just some generic subspace of Rn. And off of this subspace W, we want to talk about the orthogonal complement of W. So the orthogonal complement of W is going to be every vector in Rn that is orthogonal to every vector in W. The standard notation for the orthogonal complement is W with a little perpendicular symbol elevated. So this is to say the orthogonal complement of W, again, is the collection of vectors in Rn that are orthogonal to every vector in W. So said more precisely here, if our vector V is in the orthogonal complement, then when you take your vector V and dot it with W, you should get 0 for all vectors in your space W. So, vectors in the orthogonal complement, dot to 0. Vectors in the orthogonal complement are orthogonal to every vector in your space W. If you think, you could collect all of these vectors. By the way, let's make a note. If you think, because you might think, man, this is a really restrictive criteria for a vector to be orthogonal to every vector in your space W. I mean, that might have to be a very special vector. Note that the orthogonal complement always contains at least some vector. It always contains the 0 vector, because hell, the 0 vector times any vector is certainly going to yield 0, so at least your orthogonal complement contains that. Okay, so at least we've got something there to sort of grab onto with our orthogonal complement. But then sort of one question would be like, well, how big then is this orthogonal complement going to be? And hell, is that orthogonal complement even something well-defined with respect to vector spaces? Well, I mean, it's well-defined in the sense that it is, it has a definition that we've nailed down, but is it something that makes sense with respect to vector spaces? And I claim that it is, and here's a fact that I want us to establish. The fact is that the orthogonal complement to any vector space is itself a subspace. So the orthogonal complement is a subspace of Rn. And let's show that here, because we can show that any collection of vectors is a subspace of a known vector space if it passes the 2 subspace criteria. So the first subspace criteria is if vector 1 and vector 2 are in the orthogonal complement, must their difference be in the orthogonal complement. This is the first subspace criteria. Are we closed under subtraction? I claim we are. Because you see, first off, if these 2 vectors were in our orthogonal complement, these 2 vectors would dot with every vector in W to be 0. Well, in particular then, take V1 minus V2 and dot it with W. Since dot product distributes, well, let's distribute. We would get V1 dot W plus V2 dot W. And well, since V1 and V2 came from the orthogonal complement, V1 and V2 are perpendicular to every vector in W. In particular, they're orthogonal to this vector W. So ultimately the dot product of V1 and W would be 0 since we're bringing that vector in from the orthogonal complement, and the dot product of V2 and W is also going to be 0 because that vector 2 came from the orthogonal complement, and the long story short is 0 plus 0 is 0. So in short, any two vectors that come from your orthogonal complement, their difference would also be in the orthogonal complement. Hence, we pass the first subspace test with the orthogonal complement. Second fact that we would need to become a subspace is that if our vector 1 was in the orthogonal complement and we had a constant, just any real constant, must the constant times our vector be in the orthogonal complement? In other words, can we scale any vector in the orthogonal complement and stay in the orthogonal complement? We already know that the orthogonal complement is closed under subtraction. Is it also closed under scalar multiplication? Because if it is, then the orthogonal complement would pass the subspace test. And well, let's scale our vector here. So if we do scale of our vector, the question is, does that dot with every vector of W to be 0? And I claim that does because using the fact from the previous video, we saw that whether you scale a vector and then dot, or scale the dot product, you get the same result. And the long story short is pulling the scalar out via the fact that we saw previously, you could say that scaling the vector and dotting by any vector W would be the same as scaling the dot product of that vector times W, but that vector came from the orthogonal complement, so that vector is orthogonal to every vector in W, so that vector dots with W to be 0, and of course, any constant times 0 is 0. So the long story short is this scaled vector also is orthogonal to our W. That would hold for any W in our space because our V1 in the orthogonal complement is orthogonal to every vector in W. And the long story short then is scaling vectors in the orthogonal complement keep you in the orthogonal complement. And actually, if you really think about that geometrically, it makes sense, right? Because if the original vector was perpendicular to everything in W, then scaling that vector should not affect the perpendicular nature. The subtraction thought, if you try to think of that geometrically, is a little bit harder to do because you'd have to add these vectors head to tail, and that would be kind of funky to think about. But the long story short is we've shown, mathematically at least, that whenever you take two vectors orthogonal to everything in W, whenever you look at their difference, you get something that is also orthogonal. As I'm noticing this actually, I somehow, for some reason, turned a minus into a plus. I apologize for that. Note, it's not going to change the result because whether you're adding 0 to 0 or subtracting 0 from 0, you still get 0. But what is the long story short from all of this dialogue? The long story short is, one, that you can define an orthogonal complement to be all vectors in Rn which are orthogonal to every vector in whatever space you choose. But then now, once you establish the orthogonal complement, always not empty by the way, because you get the 0 vector in the orthogonal complement at least, this orthogonal complement itself is a space. So we could talk about any subspace of RnW and then its orthogonal complement, and the orthogonal complement itself is a space. Interesting.